We've looked at the magnetic field caused by a single moving point charge, where the magnetic field is equal to a constant mu naught over 4 pi times q, the charge of the particle, times the velocity, and take the cross product of that velocity in the direction with the vector r hat, r carré, the unit vector in the direction r, where r is what you care about. Hey. Say if we're looking at a point P here, then that would be r. Now, let's generalize this. Let's go from a single point charge to many, many point charges to a current. Now, if I were to define, let us say, a current moving to the right as drawn here, that means that since current is defined as the change in charge over the change in time, then a moving charge establishes a current. So if I've got this electron with a negative charge moving to the left, that gives me a current to the right. And if I have a lot of those electrons, and they're all moving in the same direction, with the same velocity, that's actually going to make our lives easier. Consider this. If I want to find the magnetic field for a single point charge at that point P, then that's going to change, because the magnitude for a single point charge will be constant mu naught over 4 pi times q v sine theta over r squared, where theta is the angle between the velocity and the position location. Now, this would be the same as a positive particle, a negative particle moving to the left will produce a magnetic field the same as a positive particle to the right. So if I were to write V cross R like this, then you'd see, okay, V, direction of R times the sine of that angle between them. Now, notice that the maximum magnetic field we're ever going to get in this case is equal to that constant mu naught over 4 pi times qv over r squared, because that'll be at its maximum when the velocity vector and the position vector are at right angles to each other. So sine of theta is a sine of 90 degrees, or 1. So that's the magnetic field at maximum for a single particle. If we keep adding particles in, well, there's going to be a bit of some friendly work here, because if I've got, let us say that I've got basically an infinite line of electrons that way and the other. I've got a current in a very long wire, which is approximately, at least as far as we're concerned, the same as an infinitely long wire. If I have that case, then one thing that I know is, well, actually, if I take V cross R, then just like in all those other circumstances, or the circumstances of the previous example, I have a magnetic field coming out of the board. And, okay, if I look, oh, what's the magnetic field of this electron? Out of the board. This electron, out of the board. This electron will also turn out to be out of the board. So, I've got the direction for my magnetic field right here. And if I want to find, well, there's one step I can take in the middle. Suppose I'm looking at this flow, but I want to write this in terms of the current. Well, if I take and define some differential piece of the wire, some delta S of the current, then I can define that current by, I can say, okay, well, what is the current? The current is the change in charge over the change in time. Now, if I look at this case, then if I'm looking at the change in charge as it, or charge, yeah, if I'm looking at a point charge moving with the velocity v, and I treat that as, oh, a tiny piece, delta Q, that individual point charge I'm looking at is some infinitesimal piece of the whole, times the velocity, which is delta S delta T. Then delta Q over delta T, that's the current. So I can write the magnetic field caused by a tiny piece of current as being equal to mu naught over 4 pi times, actually, let me lower this a bit. Mu naught over 4 pi times delta Q over delta T, which is the current, times delta S crossed with R over R squared. Now, that's the magnetic field of a tiny piece of current. There are two special cases we're going to look at because, hey, they're very common. If I look at the special case of this infinite straight line, now, to find the magnetic field then, this would actually be d delta B, a differential tiny chunk of magnetic field. So if I wanted to find the magnetic field at a certain point, that would be the integral of all those different little differential fields, would be the integral of, well, mu naught over 4 pi for open space is constant, so I can at least bring that out of the integral. The current is constant, so I can bring that out of the integral. And I have the integral over the wire, whatever the heck this is, of the differential distance piece, ds, times, or let's say ds times the sine of theta, divided by r squared. Now, when I write it like this, this is helpful because, the sine of theta if I have defined this as theta, then that's equal to, let's define that distance is d. Well, the sine of theta is equal to the opposite over the hypotenuse. So that's the single variable d over r divided by r squared. Actually, and r squared is not I over 4 pi times the integral of d over r cubed now, but r is now, let's define our x and y coordinate systems. So it's equal to the square root of x squared plus d squared to the 3/2 power, integrated, if we assume this to be a very long wire because it makes the math easier, from positive to negative infinity, then we have a wonderful opportunity here. The first time we go through Calculus 1, we learn ways to solve integrals in this form. You should have the skill to do that. The second time we go through this, often though, what we're going to do, let me check to make sure. Oh, good. That's all included. Oftentimes what we're going to do is simply then look up that answer in a table of integrals, and I will find out that the resultant answer will give me mu naught over mu naught times I, the current, over 2 pi d, the distance for the wire. So that's the magnetic field for a long wire. In the same way, the magnitude of the magnetic field for a loop, set up the textbook has this, hopefully going through this description makes the one in the textbook for the other one make sense. We find out the magnetic field for a loop is equal to mu naught I over 2 times the distance, and the integral actually becomes easier in that case.